And now we discuss more of the variation method. Let us recall the variation theorem, which says that if you have a Hermitian operator H defined in a Hilbert space, then the expectation value of this operator H in any state in the Hilbert space is going to be greater than or equal to the lowest eigenvalue of the operator. Mathematically, this can be written like this: the expectation value of the operator H in a state psi is greater than or equal to E0, where E0 is the lowest eigenvalue of the operator H, and this should be true for any vector psi in the Hilbert space. When the operator H is the Hamiltonian of the system, then the statement will read the following: the expectation of the Hamiltonian in any state psi in the Hilbert space is going to be greater than or equal to the smallest energy eigenvalue. The state corresponding to the smallest energy eigenvalue is called the ground state of the system, and therefore when H is the Hamiltonian of the system, this theorem can be used to find an estimate of the ground state energy. Suppose we are given a set of vectors psi I, and we can construct the expectation values of the Hamiltonian in each of the states psi I. Then we find the minimum of all such expectations. Then even that minimum is also going to be greater than or equal to E0, and therefore it serves as an upper bound for the ground state energy. Next, we consider the Rayleigh-Ritz method. Consider an n-dimensional subspace B of the Hilbert space H, and let the set of vectors phi I with I running from 1 to n span this subspace B. Then any vector psi in the subspace can be written as a linear combination of this given set of vectors phi I. For example, psi can now be written as sum over I, Ci, and the kets phi I, where Ci, the coefficient, is a complex number. Now we can construct the expectation value of the Hermitian operator H in the given state psi using this formula, and when we do that, we get the following equation. Now in this equation, you have a matrix element of the Hermitian operator H between the states phi I and phi j, and it depends upon two indices I and j, and this is a complex number as well, and therefore this is the ijth element of a complex matrix H. And similarly, in the denominator you have an inner product of phi I with phi j, which is also a complex number and depends upon two indices I and j, and therefore is the ijth element of another complex matrix S. So defining Hij to be the matrix element of the operator H between states phi I and phi j, and the matrix element Sij as the inner product of the states phi I with phi j. Now we can immediately see from the properties of the inner product that these matrices H and S are Hermitian. That is, Hij is equal to the complex conjugate of Hji, and similarly for S. And this follows from the fact that the operator H is a Hermitian operator. Not only that, we can also see that the matrix S is a positive definite matrix, which means all of its eigenvalues are strictly positive. None of it is 0 or negative. Obviously, this matrix S is also invertible. Now consider the simpler case where the set of vectors phi I are orthonormal. In that case, the inner product of phi I with phi j is the Kronecker delta function of I and j, and then Sij would be delta ij, and the matrix S would be the identity matrix. So the eigenvalues are all 1 non-zero and positive. Now, in terms of these newly defined matrices, the expectation value of H becomes this form, which depends on the complex numbers C1, C2, etc. up to Cn. So, the expectation value of the operator is a function of n complex numbers, and each complex number has two real numbers associated with it, its real part and its imaginary part. And therefore, the expectation of H in the state psi can be considered as a function either of n complex numbers or 2n real numbers. Our aim is to find the minimum of this expectation value over all possible state psi in the subspace B. For this, we have to find the minimum of this function over all possible values of the set of complex numbers C1 to Cn. To do this, we take the derivative of this expectation with respect to the complex number Ci symbolically, treating it to be independent of Ci star and all other Cj and Cj stars, and setting each of this derivative to 0. And taking the derivative of H expectation with Ci star and setting it to 0 gives the following equation. If you look at the first term, it is Hij into Cj and summed over j running from 1 to n. So this is nothing but the matrix product of the matrix H and the column matrix C, where the column matrix C is defined to be this column matrix with elements C1, C2, etc. up to Cn. Next, instead of writing there's an expectation value like this, I write lambda, and then the second term becomes lambda times sum over j Sij Cj. Now that sum is nothing but the matrix product of the matrix S with the column vector C, and therefore we arrive at the equation Hc minus lambda S into C is equal to 0, and this is called a generalized eigenvalue equation. Our usual eigenvalue equation would be Hc is equal to lambda C, but now in the generalized eigenvalue equation we have another matrix S sitting over there. So Hc would be equal to lambda times S into C. And this equation and this equation are the same if we write lambda to be equal to the expectation value of H. Now, this matrix equation has a non-trivial solution C only if the determinant of this matrix is 0. So that is determinant of H minus lambda S equal to 0. So H is an n by n matrix, S is an n by n matrix, and therefore this determinant of H minus lambda S a polynomial of degree n in lambda. And the corresponding polynomial equation will have n roots, and therefore this generalized eigenvalue equation will have n eigenvalues and correspondingly n eigenvectors. Now we use the properties of H and S, that H is Hermitian and S is positive definite. Then we can say a little more about the nature of eigenvalues and eigenvectors. The first property is that all the eigenvalues lambda are real. And the second is if Ck and Cl are two eigenvectors corresponding to different eigenvalues, they obey kind of an orthogonality relation, which is given by this: Ck dagger, then S and Cl is equal to 0. If S was the identity matrix, this would be Ck dagger Cl equal to 0. This is the usual orthogonality relation. Now the variation theorem would say that the smallest eigenvalue lambda is the best approximation for the lowest eigenvalue of H. Now, this method is useful in estimating the ground state energy if there are other considerations that suggest that the ground state is in some subspace of H. Then we can construct our trial wave function as a linear combination of a set of vectors that span the subspace, and then use the Rayleigh-Ritz method, and then construct the solutions of the generalized eigenvalue equation given by this, and then find all possible values of lambda, and from the properties of H and S we are assured that lambda are real, and the minimum of that lambda is going to be our best estimate for the ground state energy. Next, we discuss the variation method for estimating the excited state energies. Let the set of vectors phi I be the set of orthonormal eigenstates of the Hamiltonian H ordered in the increasing order of energy. That is, if phi 1, phi 2, phi 3, etc. are the eigenvectors, then the corresponding eigenvalues E1, E2, etc. will be arranged such that E1 will be less than or equal to E2 and E2 will be less than or equal to E3, and so on. Now, let S be the subspace of the Hilbert space corresponding to the n lowest eigenvalues. Obviously, the space S will be spanned by the eigenvectors phi 1, phi 2, etc. up to phi n. And our aim is to estimate next highest energy level, En plus 1. Now, the energy level E1 is called the ground state energy level, and E2 the first excited state, etc. And therefore, the energy level En plus 1 is the nth excited state. Let us first consider a general state in the Hilbert space, which can now be written as a linear combination of the set of eigenfunctions phi I of the Hamiltonian, because they are the eigenstates of a self-adjoint operator, and they are expected to form a complete orthonormal basis in the Hilbert space. And therefore, any arbitrary vector psi in the Hilbert space H can now be written as sum over I Ci, the kets phi I, where Ci are the coefficients and they are complex numbers. Now, we consider a trial wave function that is orthogonal to the subspace S of the lowest n eigenfunctions. And this trial wave function should satisfy the following property. The inner product of phi I with psi should be 0 for all states phi 1, phi 2, etc. up to phi n. Then, in the general linear combination Ci, which is actually given by the inner product of phi I with psi, then Ci would be equal to 0 for all states I equal to 1, 2, 3, etc. up to n. Therefore, we can write our trial wave function as the linear combination of phi i's with I greater than n. So it's given by this equation. Then the expectation value of the Hamiltonian can be computed using the formula as before, and we arrive at the following equation. So in the numerator you have Ci square Ei, but the summation over I ranges from I is equal to n plus 1 and goes up to n is equal to infinity. And the denominator similarly have summation ranging from I is equal to n plus 1 to infinity. In the numerator, we note that the energy eigenvalues that appear are En plus 1, En plus 2, etc. Since these energy eigenvalues are arranged in the increasing order, we see that En plus 1 is less than or equal to En plus 2. It should be less than or equal to En plus 3, and so on. And therefore, every Ei that appears in the sum in the numerator is going to be greater than or equal to En plus 1. And therefore, if we consider a series sum over I greater than n Ci square and Ei replaced by En plus 1, then that series will be smaller than the series given in the numerator. And therefore, the series given in the numerator is greater than the series in which this Ei are replaced by En plus 1. And the expectation value of H now satisfy the inequality that it is greater than or equal to En plus 1 sum over I greater than n Ci mod square divided by the same numerator. Now, this summation that we see in the denominator is in fact the norm square of our trial wave function, and obviously it is non-zero, and therefore we can divide this factor in the numerator by this factor in the denominator, and they get cancelled, and the result is En plus 1. And therefore we arrive at the result that the expectation value of H in the psi in the ket that we have chosen in the previous slide is going to be greater than or equal to En plus 1. So that provides us with an upper bound for the nth excited state energy. The next question is the construction of a vector psi that is orthogonal to the space of n lowest eigenvalues of the Hamiltonian. And this can be constructed in the following way. We start with a vector z and then construct a new vector psi using this formula. The psi is equal to ket c minus sum over j equal to 1 to n, the inner product of phi j with c multiplying the ket phi j. Now we can show that this vector psi is orthogonal to all of the phi j's where j runs from 1 to n. To see that, let us construct the inner products. Phi I with psi will be equal to the inner product of phi I with c minus the inner product of phi I with this linear combination. Now, the inner product is linear in its second argument, and therefore the inner product of phi I with this linear combination is simply equal to sum over j equal to 1 to n. Then this complex number comes out. Then we have the inner product of phi I with the ket phi j. Now we have already assumed that the kets phi I are orthonormal, and therefore the inner product of phi I with phi j is the Kronecker delta delta ij. Now consider the summation in the second term. If I is greater than n, then this delta ij is going to be 0 throughout, because I is a number that is greater than n, and j is going to range only from 1 to n in the summation. When I is less than or equal to n, however, this summation will result in the term inner product phi I with c. But this is exactly equal to the first term, and therefore they cancel each other. Therefore, we see that the inner product of phi I with psi for all states phi 1 etc. up to phi n is 0. Therefore, we have obtained our desired trial wave function.